Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, I'm revisiting the Brazilian Apple II clone that I worked on in the last video. This is the motherboard from a MILMAR Apple II Plus clone, which pretty much was a carbon copy of an Apple II Plus logo, badge, and all. After getting the power supply working, which I have right here, which took me a little bit of time, I got sort of stuck on that. The motherboard wasn't really showing any signs of life, and it turned out that it had a bad bus transceiver, which I was able to identify and replace. But that did not get this motherboard working whatsoever. It still just shows no signs of life. So in this video, well, prepare yourself because I'm recording this intro after I've already finished the repair work on this. This is going to be a very classic deep troubleshooting episode because this motherboard, it has some really overlapping subtle faults that were really tricky for me to identify. So there was nothing simple and easy about this repair. This thing made me really work for it. Very much like the last Apple II clone that I worked on, which was an unbranded one from Taiwan, that also was really difficult to get working. And incidentally, that machine does still work. It's up in my office, and that's the Apple II that I use. So prepare yourself for a video with many twists and turns, and well, at least there's a payoff at the end. So without further ado, let's get right to it. Now, where we left off in part one, this clone motherboard from MILMAR in Brazil was really showing no signs of life, at least when it comes to the video output. We did see signs of life when we took a look at the activity on the CPU, the address and the data bus. But when you turn on this computer, it looks like it was executing code, like we could see it going to the ROM chip, and yet there was no initialization of the part of the memory that's used for video. Now, as a bit of a refresher, the Apple II motherboard, and this is just a clone of the Apple II and the II Plus, as soon as you power that system up, even if you have no ROM and no CPU, the hardware on the motherboard is going to start reading from the main RAM and displaying into the screen. That just happens automatically if you have a good clock. When the CPU is able to read from the ROM and start executing code, what happens pretty early on in the boot process on the Apple II is that it will change the video display mode to text mode, because I think the Apple II always boots up in a graphics mode generally. So it'll change to text mode, and then it will erase the part of the memory that holds the text page one, fill it up with spaces, and then put the Apple II banner at the top, beep the speaker, and start the boot process. Well, that part of our boot process is not working, and we have to kind of figure out why the computer looks like it's trying to do stuff, like it's accessing the ROMs, but it's not getting to the phase of the boot ROM where it's actually writing to the system memory to initialize it. And actually beyond that, if we think about it, and we'll just look at the screen that this thing is generating in a second, it's pretty much never even getting to text mode. So it really feels like the CPU is not even executing any of the ROM code. I don't know how early it is in the boot process with the Apple II ROMs, where it switches into text mode and tries to erase the screen, but I'm presuming that's relatively early in the boot process, and we can tell that it's not even getting to that point. And this is what I'm talking about. So if we turn on the system, we just have this kind of semi-graphical corrupted screen, and we're looking at some color there, and I'm pretty sure what we're seeing here is just the initialization state of the RAM when you first power it up. RAM always initializes to some state, usually with sort of stripes. Now we can actually do a little proof of concept here by just removing this ROM chip, and this is the F0 ROM chip. This is the one that contains the boot code when the CPU starts to execute when you first power it up. And I guarantee you when I turn this on, it's going to look exactly the same. Yeah, it does. So nothing in this ROM actually had any kind of effect on the RAM. Now this is where with an Apple II type system like this, it's kind of difficult because you just have no visual feedback as to what's going on. Is the CPU actually running code out of the ROM, and then the ROM code is telling the CPU to erase the RAM, to clear the screen, but maybe there's a problem with the interface between the CPU and the RAM that's breaking that? I don't think it's that, because if the ROM were actually working but just weren't able to write to screen memory, well, we would have a beep out of the speaker, and we're definitely not getting any kind of sound out of the speaker whatsoever. So we really have to kind of figure out why the CPU is seemingly getting stuck and is not executing any code. There's a few things we really need to check first. We checked in the last part that we have good clock, we have good power, we have good reset signal, so that's all good. The CPU's got what it needs to execute code. We also fixed the bus transceivers for the data line, so we know that that's working by replacing this 8T28. And we were able to validate using the oscilloscope that all the address lines that are on the ROM chip are looking good. They look correct from what the CPU is trying to do, because the CPU needs to be able to address the various ROM locations so it can execute the code out of it. Now, one of the things architecturally about the Apple II is that Woz designed this thing to have DMA capabilities, direct memory access. And what that means specifically is you could have a card plugged into one of the slots and it can assert a signal which will disable the CPU temporarily and then allow that logic that's on the card to directly access the RAM. To facilitate that, because the 6502 normally doesn't support DMA, you need to be able to stop the CPU and disconnect it from the data bus and the address bus. Normally a 6502 is always driving the address bus, so you have to have something in between it and the rest of the motherboard to disable those address lines. That is something that a lot of other 6502 based systems don't have. Well, at least ones that run a normal stock 6502. Think the Commodore VIC-20 as an example. But if you look at the Commodore 64, it does have DMA access, but that's facilitated by the fact that the 6510 CPU on there, the variant of the 6502, has a signal that you can assert that does do this DMA function where it disconnects the CPU from the data bus and the address bus. So what I want to do is I want to make sure that all of the address lines that are going to those drivers that go between the CPU and the rest of the motherboard are working properly. We took a look at all the address lines on the ROM chips in part 1, and all of those look good. But these are only 4K ROMs, and therefore they are missing a couple of the address lines, I think 3 address lines up at the top, that potentially maybe aren't getting through. And that could cause issues with the entire memory map on the system being stuck at, say, 4K, where when the system goes to write to something like the speaker, that's up in the C000 location on the Apple II. That's where those soft switches are for the speaker and switching graphics modes and stuff. If we have a problem with one of those address lines in the upper regions, it's never going to be able to actually write to those. So we'd never hear a beep, we'd never see the screen mode change. And you would think theoretically that it would be showing something on screen, like we should see a change. But maybe what we're looking at here is like page 2 on the graphics mode, and the ROM is only going to write to page 1 in the text mode. So maybe that's why we're not seeing anything. Now this motherboard, while it's a clone of the Apple II Plus, it's obviously not identical because it uses 3 ROM chips versus 6, and the original ROM chips on the Apple II Plus are like these mask ROMs with a non-standard pinout, and these are just normal EEPROMs. Same for the character generator. So stuff has changed a little bit, so we need to kind of validate how the CPU address lines are connected to the rest of the system so we can check those 3 additional address lines up at the top. Now to do that, I'm going to use the book, The Apple II Circuit Description by Winston D. Gaylor. Great reference anytime you're working on an Apple II or II Plus. Tons of theory about the exact way this thing works, but it also has some schematics in it, and it goes over the differences between the different versions of the original Apple II and the II Plus motherboards, because there are actually, I think, 4 or 5 revisions of those motherboards, and there are some subtle changes between all of them. Going to page 203 in the PDF will show us the CPU, and we can see up at the top, these are all of those 8T28s that are for the data lines. You know, we swapped out the bad one there. And then these are for the address lines, 8T97s. Now there appear to be 3 chips that make these up, H5, H4, and it looks like H3. And looking at this motherboard, well, right off the bat, it looks like, well, this is H up here. So there's an H there on the board. And obviously there's no chips there. So I think the numbering changed a little bit. G is what we're looking for. So G, 3, 4, and 5, these 3 chips is what it indicates. Now these chips are 74LS 367s. Now somewhere in the back of my memory, I'm kind of remembering that 1897s and 74LS 367s are equivalent parts. I think back in the day when people were working on these systems, the different logic families like these 8Ts and the 74LS, everyone kind of knew what the equivalent parts were, but these days we've all sort of forgotten that information just because the 8T stuff is not common at all. Here's the PDF for the 74LS367, and it is a hex 3-state buffer driver. So basically looks the same as what we're looking at here. So a non-inverting buffer. There's no little circle on the in or out of the little triangle. There is on the side here, but that's for the logic signal that turns it on and off. And we can see that it matches this. This thing has 2 select signals, G1 and G2. One selects 2 of the gates and the other one selects 4. Don't really know why it's not 3 and 3, but there's probably a reason for that. Either way, the little circle there means that when this logic signal is low, that's when it's actually turning on all of these buffers. And you can kind of see that in the truth table right here. So if the input, which is A, is low or high, and then G, which is the turn on signal, is low, then it will just pass through whatever the signal is. If G is high, then it doesn't really matter what A is. That's what the X means. And the output is high impedance. So it's no longer driving the bus. That's this DMA thing I was talking about. And I think we can see that on here. Yep, right there. From peripheral IO, DMA. So this 22, this is what drives these signals. It goes through at 74LS04. And that turns off all of these signals. Oh, and also the read-write signal coming from the CPU. And when it comes to the EEPROM, when we took a look at all the address lines, this goes up only to address line 11. So specifically, we did not look at actually 12, 13, 14, and 15 plus the read-write line. So these 5 signals are the ones that we really need to make sure are making their way through these buffers. We did not check that. Now, one thing I'm not sure about, and that's why I have the multimeter out here, is we need to make sure that these are even hooked up in the same way as the original Apple II Plus, because they could have easily just swapped some stuff around here when they redesigned this motherboard. So what I'm going to do is I'm going to start with the read-write signal, which is pin 34 on the CPU, and it should go to H5 on pin 4. So that's there. H5, that's the one, this one here. Pin 4. Oh, good. Okay, so that has continuity. Now I'm on pin 25, which is address line 15. That's this right here. We want to make sure that goes to H4 on pin 14. 14, there it is. Good, we have continuity there as well. And why don't we go to address line 0 here, pin 9 on the CPU. And let's make sure that we go to H5, pin 12, which is this one. And good, we have continuity. So pretty much looks like the design of this clone motherboard matches the original Apple II motherboard. So what I need to do now is we need to fire this thing up because it's not running right now. And then we just need to take a look at address line 12, 13, 14, 15, and read-write, and just make sure that we have outputs on all of these buffers. I already know the CPU is generating these because I checked that in part 1. We looked at all the address lines and read-write, and we had activity on all of them. But if one of these buffers is bad, for instance, like A12, then 3 won't have any output, but we will see input on pin 2. Actually, you know what I should probably do is I should probably just go through all of the pairs of these pins. Because we look at the datasheet for this, we're going to have inputs and outputs. So 2, 3, 4 is an input, 5 is an output. All I need to do is just go through each one of these pins and check to make sure that we have outputs on all of them. And when I do it, I need to check that the output is available on the actual socket itself. So I'm touching the socket right now, and you can see that we do have a signal there. I'm not on the pin on the chip, because what if there's a bad contact from these oxidized pins? So this is pin 2, and we can see how it looks. And then that's coming from the CPU. And then this is the output, and it looks a little bit more jaggy on the top. That's fine. That's the output from this actual chip itself. So let me just go down and just check to make sure we have those pairs all the way along. Now we do know that we have how many? 18 of these buffers. And if we look at the schematics, there is an 18 here. It looks like we only have 17. So that means that we have one extra buffer that's probably just not used. So we're going to find one of these that won't have an input or an output. It's hard to tell right off the bat which one it is. I think it's H3. 9, 10, 11, 12. Yeah, it looks like H3 is missing the 13, 14 pairing, because see H4 and H5 have it, but there's nothing for H3. So let's just go through all of these. So the system is running right now, and I'm just going to make sure that we have all those pairings. And like I said, I'm touching on the socket itself, not on the chip, just to make sure that we have all the ins and the outs. We can always tell the ones that are the outputs because they're actually driving it higher than the inputs. So the CPU on this computer, some of the outputs are kind of low, like 3.5 volts. We saw that when we were looking at it in part 1, but the output of these chips is always much higher. I mean, we can ignore that noise on the top. It doesn't really matter. So I'm on H5 right now, by the way. There's the CPU. And so H5, yep, it's got everything on it. All of those pairs are working. And now I'm on H4. And it looks good as well. Okay, so far, so good. I am now on H3. Everything looks fine. You know, matters to just check everything just in case we have a bad connection here, because that could definitely render this system inoperable. Okay, here's the dead one, or not dead, it's just not used. So we switch this back to auto mode. So I'm on pin 14 on H3, that would be the input side of the buffer, and it's just floating. Funny, they didn't hook it up to anything. They should have hooked it up to ground. The output is high, but I assume the output of this is not hooked up to anything. It's bad practice to leave the gates just floating this way. You should tie them to ground, but I guess Woz thought that that wasn't necessary. I mean, there aren't even bypass caps on this motherboard, and there aren't on the original Apple II either, so it seems like from a best practice standpoint, Woz was definitely, well, how shall we say it, I guess, not following best practices, and yet the system works. So it kind of shows you how resilient this stuff actually is. Right, anyways, I went through all 3 of these chips, and other than pins 14 and 13 on H3, which don't seem to be used, all of the other ones had stuff on the input and the output. So that shows us that all the address lines and the read-write line are at least getting through these buffer chips. So that's great. So that confirms now that we have everything looking good on our data lines and we have everything looking good on the address lines. At least the system kind of has what it needs to work. Next, for this system to actually execute code out of the ROM, what we need to have happen is the ROM itself, needs to be good. And I can tell you that before starting shooting even part 1, I did dump these ROMs just in case I damaged them or something, and I didn't know if they had custom code on them. So I dumped them all with my EEPROM programmer, and all of them just worked fine. It was able to read out the contents of them, and byte for byte, they were a match for just Apple II ROMs. So this motherboard is just running stock Apple II Plus ROMs and character ROM. All of it is just 100% stock, because remember, in Brazil, ROM code is not copyrightable, at least at the time when this motherboard was made, so this isn't even illegal what they did here. But the F0 ROM, that's the ROM number 3 on here, that's the one that's used for booting the system. It definitely is reading properly, so it has the correct information on it, so it's not bad in that regard. But we need to also make sure that it's being selected properly and that not one of the other ROMs is also being selected. Think back to the Commodore 64, when the PLA fails, what can happen is it can select multiple things at one time and you end up with bus conflicts. I don't think that's happening here, because we would see that on the data bus. We'd see like weird low levels as like 2 things were fighting against each other, and we really don't see that. But it's still worth checking to make sure that on these 3 ROM chips, only one of them is actually being selected, and it should be the F0 ROM. That's the one that's used to start booting the system, and the other 2 ROMs should never be actually accessed. So looking at our ROM chip here, we have 2 chip select lines on the 2732 EEPROMs. There's pin 18 and pin 20. Now, I know it says G and E. These change name depending on which manufacturer you're looking at, but one's usually like output enable and the other one's like CS for chip select. In any case, you gotta have both 18 and 20 low at the same time for the ROM to actually be selected, which means it will drive the data bus depending on how the address lines, which is the input, is configured. It'll output what it's stored in as content at that location on all these Q lines. That's the data bus lines. So we gotta check that the F0 ROM has both 20 and 18 going low sometimes, not all the time, but sometimes, and that also the other ROMs don't have any activity on those lines. With the Apple II, I just happen to know this. When it starts to boot, everything that's happening is running out of the F0 ROM. This is the one that initializes the system and bootstraps it. The other 2 ROMs are used for AppleSoft Basic. So if it was getting to Basic, then we'd see activity in these as well. But I don't believe it's actually getting there, because we don't have a beep, we don't have, any kind of activity on the RAM. So let's just check these chip select lines and see what we see. Okay, so here's pin 18. Plenty of activity. It is weird how it's like in repeating patterns. Let's turn the system off and on. So just sort of looks the same. So that's 18. This is on ROM 3, the one that should be selected. And this is pin 20, and it looks good as well. Now if we go to the next chip over here, so this is pin 20, and there's nothing happening there. And pin 18, same thing. Let's turn it off and on. Let's make sure that it's not accessing it for some reason just at the beginning. In fact, we'll set normal triggering mode, because, yep, if there were any activity, you would see it there. But this is triggering just because of the transition between low and high as we power on the system. So that was pin 18, and let's try pin 17. Powered off, powered on, nothing. And finally on ROM 1, same thing, nothing's happening on these 2 chip select lines at all. Yep. Now if I check one of the data lines, because these are shared across all the chips, we have plenty of activity and it is triggering fine. It's just not on the chip select lines. Okay, so chip select seems to be only selecting ROM 3, which is correct, and not these other 2. So that doesn't appear to be our problem. So from what I can tell, this system really has pretty much everything it needs to start running code. But there's still one thing we haven't validated. Let's jump over to the 6502 datasheet, and I'm just going to talk a little bit about what's required for any 6502 based system to actually work. So one thing about the 6502 that's interesting is that it's a very budget CPU, so to speak. And when it came out in 1975, it was very inexpensive. But because of that, it does have a couple of requirements that might catch people off guard. The Achilles heel of the 6502 processor is that it requires RAM to even work properly. Now, it can work in a very reduced functionality mode without any RAM, like say you just have ROM. But generally, when people write code for the 6502, it needs RAM. Now, one of the reasons why is right here, 0-page addressing. Zero-page addressing allows shorter code and execution times by only fetching second byte of the instruction and assuming the zero high address byte. Careful use of zero-page addressing can result in significant increases in code efficiency. What it's talking about is the fact that any type of RAM access, it's going to have a 16-bit address. So ABL, that's low, ABH for high. Well, zero page is the first 256 bytes of RAM. Now that, if you just look at the very first address, is 0000. And if you go through the first 256 bytes, everything is going to be 00 all the way to FF. So the low byte is the actual 00 through FF. That's the address in that first page. But the high byte is always going to be 00, and that's the zero page in the 00. So you can save time in the execution of your code, and you can make your code smaller by using these instructions for the 6502 that reference the zero page. So all you have to specify to say, like, load this memory location into the X register, you only have to specify one single byte because you're only specifying the low byte, because it just knows you're talking about that RAM that's in the very beginning of the address space. Well, I can tell you that when the ROM designers for most 6502 systems were writing their code, they pretty much always have the assumption that that zero page of memory is working correctly, that first 256 bytes of RAM. And when it doesn't work correctly, the system doesn't really work properly. And that's because at the very beginning of the boot process, it's using a whole bunch of zero-page opcodes. And of course, it's going to be storing and reading memory from that first 256 bytes of RAM. And if it doesn't work correctly, well, the system is really just not going to work at all. But beyond that, there's another part of memory that's absolutely critical for the 6502 to work properly. And the stack pointer register is, well, an integral part of that. Now, if we look at stack pointer, the stack pointer is an 8-bit register used to control the addressing of variable length stack on page 1. So instead of page 0, which is just the high byte being 00, it's talking about page 1, which is 01. The stack pointer is automatically incremented and decremented under control of the microprocessor to perform stack manipulations under the direction of either the program or interrupts, so non-maskable interrupt or the IRQ. The stack allows simple implementation of nested subroutines and multiple level interrupts. The stack pointer should be initialized before any interrupts or stack operations occur. Right, so to boil that down, anytime you're trying to use any kind of subroutines in your code, which would be like, say you're executing and you go jump off to somewhere else to say do something and then you return back to where you started from, that is using the stack. What the processor does before jumping over to a subroutine is it takes the current program counter, that's the location in RAM that the program or the CPU is executing from, and stores it in the stack. Then the processor jumps over to do whatever it's going to do. And then there's an RTS instruction, which is like return from subroutine. And it takes the program counter that's on the stack, which is RAM, right? It's in that page 1. It puts that back in the program counter and then it continues execution. Well, what if your page 1 of RAM is not working? Like it's got a bad bit. Well, what happens is the processor goes and stores that program counter into RAM, and then when it reads it back, it gets back something that's different than what it's stored there. So when it goes to resume execution, the processor, instead of resuming from, say, somewhere in the ROM code, jumps off to somewhere random and then gets stuck in a loop, or, who knows what happens. Something bad happens with the execution. And when we look at the data lines and the address lines, we saw like a lot of repeating happening, which kind of implies the processor's like stuck in some weird zone. So what it all boils down to is that for the minimal viable configuration of any 6502-based system, you need at least 512 bytes of RAM. That would be zero page and the page 1, which is for the stack. Now, I can hear people saying right now, hey, the Atari 2600 only has 128 bytes of RAM. Now, I think that is true. And if I recall, part of the registers for the graphics chip, I think, and maybe the sound chip, is in the zero page, which allows fast code execution, actually. But then I think there's 128 bytes of RAM in the second half of that zero page. So that allows it to store, your score and stuff. But I don't think the 2600 actually has any RAM in the stack area for the 6502. So that doesn't mean that the processor can't work. It just means you don't have access to subroutines and stuff like that. So when I say you need like 512 bytes for a viable system, I mean, if you want full functionality of the 6502, that's where you need to have 512 bytes. You can obviously get away with less if you just, work within exceptions. Now, when it comes to the ROMs that are on the Apple II, which we know that this system is using, it definitely makes use of the stack right off the bat. Like it initializes the stack pointer and starts using it for subroutines and whatnot. And it's also using the zero page. So if you have issues in your first 512 bytes of RAM, the system is definitely going to not behave correctly, and it's going to do strange things, like it's going to crash, depending on how the RAM is bad. And that's where things like the Commodore 64 dead test ROM come into play, because the 64 is no exception. It also needs that 512 bytes of RAM at the beginning to really even start to initialize the system. So when you use the dead test ROM, or even DES test, DES test, which is a better, improved version of that dead test, it has special code in those ROMs that is able to test that first 512 bytes of RAM without relying on the stack or the zero page. So it runs entirely inside of ROM code, and the subroutines are all unrolled. So it doesn't need to actually jump to subroutines. It's just able to run this code, and it can do jumps. You can still jump within code. You just can't jump to subroutines. So as long as you unroll everything, so you don't use those subroutines or whatever, you can run the system without the stack and without the zero page. And that's how those initial phases of the diagnostics work. So I think that's what we need to do on this machine, is we really need to run the dead test ROM, the Apple II dead test ROM, that is, to properly test that first 512 bytes of RAM to let us know if it's working or not working. Because we could have a myriad of problems like bad RAM chips, bad sockets, bad logic around that RAM, all sorts of things that would prevent that part of the RAM from being accessible or usable by the CPU, that would then immediately just crash the execution of the stock Apple ROMs. So for the dead test ROM, and I've showed this off on the channel before, but just to kind of reiterate, this is exactly what the purpose of this ROM is this diagnostic ROM, which was really written by my friend David Giller, but it's on my GitHub repo. What this is able to do is able to do a really thorough RAM test using MARCH-U RAM testing on the entire RAM on the system, all 48K. But more importantly is when you first power up, it has a whole section here that specifically tests the zero page and the stack. The ROM will test zero page and stack using MARCH-U, one of the best RAM tests available, and it will catch page errors and zero page stack errors. And it's going to test addresses 000 to 1FFF. And if any issues are detected, it will beep out an error code to indicate which bit is bad. So 1 beep is data bit 0 and 8 beeps is data bit 7. And there is a little handy diagram right here which tells you exactly which chip is which bit. So 1 beep is this chip right here, and all the way through 8 beeps being this chip right here, if there is a problem accessing the beginning of memory. Now, if there's a logic issue on the motherboard or bad contacts or who knows what, we might get false stuff, like we'd get different beeps every time, and there might not be a problem with the RAM chips, it might be a problem with somewhere else. But this is a good start to know if this machine can even run code, because so far we haven't seen it do anything. So to download this, just go to releases, click on version 1.01, download this ROM chip right here. It's 2K in size. There's also a disk-based version. If you have a system that kind of mostly works, you can still boot into DOS. You can load this and it will just load into the language card and then execute the ROM as well. But this 2K ROM is what we need. Now we know these are 4K ROMs on here, so we're just gonna have to double this up in the ROM, just write it twice into it. And we'll use the TL866, we'll set it to 2732. I'll just load Apple II dead, and I've downloaded this a few times, obviously. First, we're gonna load it just at the beginning of this ROM chip. Now, the problem is it's loaded a 2K ROM into a 4K file, and you see the upper part here is just all blank. So all we do is look at where the split is, and it happens to be 800, because if you go up here, the top of the chip is FFF, divide that by 2, you get 800. We're gonna turn off the fact that anytime you load a file, it clears the entire buffer, so we have to disable it, and we're gonna load this into 800. So type in 8 there, hit OK. And now, so here's the original load, and if we scroll down, there it is again. So now it's in here twice. And realistically, because we need this to be accessible all the way at the top of the memory space, we really only need to load it into 800. But if you aren't sure, just load it in multiple times. And if we go all the way to the top here, you see these hex values that are in here? That is the reset vector. When the 6502 starts up, it's going to look to the very top of the address space, which is FFFF, well, a little bit down from there, and it's going to use this to jump to execution of the ROM. It's going to be jumping to F800. Well, that happens to be exactly 2K below the actual top of memory space, which will jump directly to this right here, 78DE D8. It's going to start executing code right to there. So I have a chip in the program already. I'm just going to hit program and let this flash. Now, if you have an Apple II and you can't just use normal EEPROMs, then I totally recommend getting one of these one ROMs. This is a 2350, a Raspberry Pi 2350, and it emulates any of the ROM chips and EEPROMs and whatnot. It's very easy to program using USB-C. You don't need any special hardware. You just plug this into the motherboard and you're off to the races. These are great, and you can even have multiple ROM images in here. Plus, one of these can serve up multiple ROM chip sockets at once. You just put little flying leads between the sockets onto these extra pins, and this one thing can emulate like 3 ROMs at once, I think. Maybe even more. I don't remember what Pierce has done with this thing, but amazing project. I won't need to use it here because we are just using standard EEPROMs. All right, one thing I recommend, by the way, is overburning these old EEPROM. So this is a 21 volt EEPROM, and this programmer, while it can do it, this is a TL866 3G. I recommend programming it multiple times. I've had issues where it doesn't quite do a perfect burn, and while it verifies correctly in here, in the actual computer, it doesn't really work correctly. So just programming this multiple times kind of helps make sure that it's got a nice solid burn inside the EEPROM. All right, here we go, moment of truth. Are we gonna get beeping? Are we gonna get nothing? Let's see what happens. Okay. There we go. It's telling us we got bad RAM. So this is our first signs of life out of this thing we've ever had. Okay, so as for the beep code, we had like a long beep and then a short beep. One long low beep followed by a number of medium beeps. This is the 0 page or stack error. Count the medium beeps to tell you which bit is bad. Well, we were getting one short beep. Let me turn it back on. So that boop, that's the one beep. Right, so it's telling us that this first chip, which is an AMD chip, is bad. Now, what it does not do is it will not tell you that all of these chips are bad. It just stops on the first one that it finds is bad. And it's telling us that it's this one right here. Now, what I think I'm gonna do is I'm just gonna swap another random chip into that position. Now, these are Motorola chips up here. This is the top bank of memory. Let's put one of these in there and let's deoxit the socket as we do it, since everything is very crusty, and it could just be a problem with, crustiness in the socket, right? But we're gonna pop this in there. I wanna see if anything changes. If we put this in there and it's still beeping exactly the same thing with one long beep, then that tells us that we have a problem elsewhere. But here we go, let's make sure it's in correctly, turn it on. Right, same exact freaking beep. And what are the chances of this Motorola chip being bad? Very low, if you ask me. Now we have two beeps? Wait. Okay. Well, is that just a red herring? Like, I don't know. It was. Okay, now we're back to bit 0 being bad. So I really feel there's a problem elsewhere with this thing. There's got to be a problem elsewhere. So I'm going to swap this Motorola chip back into its original socket. And you know what? Anytime I take something out, I'm going to deoxit that socket. Just because. I mean, I might end up having to deoxit every socket on this thing. So we figured out a few things for sure, is that it's beeping 0 or, bit 0 or bit 1 sometimes. And I don't think either of those chips are bad, because I swapped, that one chip over and it made no difference whatsoever. And it's super unlikely that a Motorola chip would also be bad in the same way. So I think it's time to go back to the circuit description book and let's take a look at the RAM section so we can start to understand which chips are relevant for RAM. Now here's what's interesting. So these types of RAM chips, 4116, they have an input and an output for data bus. Sometimes on some computers they're just hooked up together, those two lines, but it looks like the Apple II uses them separately. So the D0, this is the input that goes into these chips, or D0 through D7 from microprocessor. And then it comes out of these 74LS174s, which are latches. And you can see 2 peripheral IO and video generator. Well, obviously that also is going to the CPU itself, because the CPU itself is going to be reading from the chips. It's going to be reading it off of these pins. I'm pretty sure it is, at least. Now on the motherboard, those two chips are right here. Now I'm pretty sure if I take these out, what's going to happen is we will see nothing on screen, or just be all white. So let's take these out. This is B8 and B5. And we turn on the system, and yes, we have a completely white screen. Kind of as I would expect. Maybe what I'll do, and these chips are not tarnished, by the way. They actually look really good. I'm going to swap these around into the different sockets. And let's see if that makes any difference to what we're looking at on screen. Nope, it does not at all. Pretty much, I mean, we have what we had before. It's still telling us that data bit 0 is the problem. So I'm going to say that those aren't our problem. If one of these were bad, I would think we would have a difference in what we see on screen there. Like, I don't know, the junk on screen will kind of move positions or something like that. But you know what? Thinking about this a little bit more, I'm going to unplug the speaker so we don't have to listen to this. I'm thinking that maybe we have an addressing issue, because the way the Apple II displays RAM on screen, it kind of happens in rows. And we talked about this in the Apple II GS repair video that I recently did. My assumption is when the ROM writes to the 0 page and the stack, we shouldn't see anything on screen, because the stack and 0 page is not anything to do with what's displayed on screen. The screen memory is further up. I think it starts at like 400 hex. But the fact is we see little bits of stuff getting written there, which is kind of telling us that when the CPU tries to write to stack and zero page, which is all that's happening right now, little bits of it are getting written to the wrong place in the RAM. And that is what you would call a page error. That's an addressing problem. That means that when you're writing to one location in memory, you're actually writing to multiple memory locations at the same time, or the wrong location at the same time. And when you say page error, because say you go to write to the 0 page at address 000, and then you write to something in the stack at address 100. Well, if there's a page error, when you write to 000, it can also write to 100 at the same time, or vice versa. And maybe when we're writing to 100, it's also writing to 400. And if we take a quick look at the Apple II memory map, we can see right here, yeah, text page 0, 400. So 00 to 00FF, that is 0 page. Then we have the stack, which we've already talked about. Then we have some stuff that's required for like AppleSoft Basic and whatever to work. And then we have the text page. But it definitely looked like while I was testing the first 2 pages, stuff was getting written to 400, which definitely implies we have a page error. So there's something wrong with the addressing to the RAM, and that's definitely going to cause it to fail its RAM tests and also prevent the system from booting. So I don't think our issue has anything to do with the data lines at all. So I took those chips out unnecessarily. The problem is most likely to have something to do with all of the chips that generate the RA lines. This is the RAM address bus lines. These are multiplexed. So let's think about the addressing error. If we take a look at this page 1 or part 1, this seems to have only high address lines, right? 12, 13, 14, and 15. And if we look at the binary representation of 400, the relevant bit that is potentially bad is this one here. So this is address 8910, A10, and there might be others as well. Where I'm going with that is when we look at this page, I don't think any of these address lines are relevant, because if one of these were stuck, we wouldn't have a replication of the 0 page or the stack up to 400. If you think if this address line 10 were stuck, so say you're writing to address 0000, which is 0 page, that would be all zeros. But say this line were not working properly and it was like always 1, then anytime you wrote into the 0 page, it would also write to 400. So that's the hunch I'm going to go off of. So we need to look at this part 2. Now I opened up a second copy and I rotated it so we can see which chip specifically is handling address line, what did I say, 10? Looks like it's this one right here, E11, 74LS153. 74LS153. Well, let's take this chip out and let's see if that has a visual change on the system, at least when that RAM check is running. Okay. Well, and let's plug the speaker in. I bet you it's going to be doing the same thing. Yeah, 1 beep. So it's interesting. It's a little different now. Obviously, the pattern we're seeing is different, so I'm not convinced this is necessarily our culprit. Let's deoxit that socket and put it back in, see if it goes back to exactly where we were. Yeah, it looks exactly the same as it was before. Now there happens to be another one of these chips sitting right next to it. What I want to do is I'm going to swap these 2 around, and I want to see if that changes anything in the image we're looking at. Because if, for instance, there were a problem with this chip, like it was bad, then I would expect it to change. No, it looks exactly the same. And I'm sure we're going to be getting the same bad bit. Yep, we are. Yeah, power cycling off and on looks exactly the same. Okay. At the moment, I'm kind of stumped, just sort of thinking about what's going wrong. I think the evidence I need is on that screen, the one that comes up when the diagnostic tries to run, how there's little specks of junk all around. I really do think this is some kind of an addressing error. So interesting is looking at this schematic, if we look down here, AD signals are from microprocessor and H and V are from the video generator. So there's all the H and V stuff. This has to do with how the video circuitry refreshes the RAM. Well, it not only refreshes it, but I mean, it's actually outputting what's coming from the RAM to screen. That's happening, whether the CPU or the ROM's in there or not. And really, when it comes to the addressing of the memory, well, we can see all the address lines right here. So we have some clock signals, horizontal, that's coming from the video circuitry. We should probably just look at all the signals going into these 74LS153s, just see, kind of do a sanity check just to see what they look like. And the multiplex address lines that go to the DRAM, remember they're coming from two different places. And if we look at the DRAM again, so there's A0 through A6. 0 through 5 are shared between all of the chips, but 6 is actually unique, and that comes from the same circuitry that generates the RAS and the CAS lines. So this is part 1. Oh, and this is actually kind of interesting how RA6, that's the 6th address line that goes to the DRAM, well, it's coming from this chip, but they're all just hooked up together. I don't know where they're routed separately. I'm assuming it had something to do with the way these jumper blocks worked. I mean, they're all hooked up together here, but I think if you flip this around to the 4K configuration, I think each one of these would go up to one of these lines or something like that. Okay, well, I think I need to start reducing the amount of chips that are on here down to the bare minimum. I know that I really only need one bank of memory for this thing to work, so I'm gonna completely remove these upper two banks. Because what if we have a bad chip in one of these that is somehow, I don't know, causing some corruption on the address lines or something like that? Actually, I said I was going to look at the address lines. I think I already did. We did that in part 1, but I haven't done it again in part 2. But I'm just going to take these out anyways. And I just want to make sure that nothing changes when we run the diagnostic ROM with this memory removed. It's not needed for the system to work. You can even boot to AppleSoft Basic without these two banks of RAM. You just need that one bank at the top here. Or the bottom. Okay, so let's see. Does that change anything? It's telling us that the second bit is bad right now, but looking at the way it looks on here, looks exactly the same. So no change there. All right, with the middle bank out, no change. Okay. Oh, it was actually telling us a different bit was bad there. Let's turn it back on again. I turned it off too soon, but it sounded like it was going to tell us that bit 2 was bad. Data bit 2, that is. So 0, 1, 2, so 3 beeps. Could have been more beeps, and I shut it off. Funny how visually it looks a little different now. Now, I think if the ROM weren't in there, it'd look exactly the same. Now, with this diagnostic ROM, I don't remember, it doesn't really say on the GitHub repo what it does when it's stuck in this loop where it's beeping out the bad bits. Is it supposed to be changing the screen, or is that just a side effect of some other problem that exists on this motherboard? I'm actually not sure. Now, one thing I wish this ROM did is, before doing any kind of RAM testing on the 0 page or the stack, which is where it's getting stuck, I wish it would at least try to switch to text mode and write some characters into the text page, because visually that would help me understand, like, if there's an address error, like where it's looping or where it's repeating. Now, for grins, I'm just going to take out all of the first page of RAM too, all this entire first bank. And we're going to look at how it visually looks on screen without any memory installed whatsoever. I have a feeling it's just all going to be a full white screen. Okay, so it's all out. Yeah, full white screen. And I'm sure the speaker's just going to be telling us the same thing, just like bit 0 or whatever. Yeah, bit 0. So what I'm going to do is I'm going to put all the RAM, which is the Motorola branded RAM that was in this top bank, I'm going to put this into this first bank. These chips are pretty tarnished, but let's see what visually that actually ends up looking like. I'm kind of curious how this will look. I think the pattern should look different because it's a different brand of RAM. Ah, yeah, it does look different. I'm sure we're getting the same exact beep though. Yep. But if we take out the ROM, so there's no ROM, I bet you it's just going to have stripes. Kind of like we just saw. Oh, just a solid white screen. Interesting. I turned it off and on, and now it looks like that. Okay, so I'm kind of stumped on what to do next. So I think what I would like to do is just write up a very simple ROM replacement for this machine that simply tries to switch to text mode and fill up the text page with a bunch of characters from the character generator. I think this will be helpful because if I can get this thing to show some text, then I know, well, I can hopefully be able to examine the pattern of what I should expect to see using an emulator versus what this machine is actually doing, if it can even get to text mode. Because I just don't believe that the diagnostic ROM, the dead test ROM, is really doing enough in this early phase. I wish it did a little bit more than it's doing now, but it's clearly identifying that there's a problem with the RAM, but it isn't giving me any clues as to what's causing it. Because it's not the chips itself, it's something upstream from those. And I really do think it's some kind of an addressing problem that's happening here, but I'll know that for sure if I'm able to write a known good pattern to the screen. So yeah, let me work on that for a second. It should be relatively easy, even with my barely capable assembly language skills. Okay, so I copied some of this code from the dead test ROM itself. So here we have text set, mixed clear, low res screen, low res speaker. This is the actual beep. This is going to be a 2K ROM starting at F800 again. We're just forcing it to text page 1 with these instructions here. And then we're going to try to beep the speaker. Now this is using a branch not equal to do the beep. And then after that, it loads 00 into the X register, then it transfers that to A, and then it stores A into each one of these memory locations offset by, well, 00, because that's where it's starting. And then it just increments X, and it keeps repeating this. So all it's going to do is every time it increments this like 01, it's going to store it to 401, 501, 601, 701, and it's going to store 1 because it took the X register and stored it into A. So it's going to store that just throughout this, all 256 bytes, and it's going to do it 4 times all over again. And it will just keep looping through until it's filled up all the memory with from 00 to 256. So it's going to load all the characters from the character generator, which is going to include like flashing, inverted characters and stuff like that. And then it just goes into a loop at the end just to freeze. So we just want to fill the screen and stop. And then this stuff here is just padding. And then this is the reset vector. So basically how to jump into this code. And you can load a custom ROM into AppleWin. That's the emulator I'm using here. And there it is. Okay, so this is the way it should look on this machine if there's no addressing errors, if all the RAM is working in that 400 page, 500 and 600. I'm pretty confident in saying that what we see when we run this on the real hardware is not going to be this right here. Okay, so I'm going to flash a new EEPROM with this ROM code. It's really tiny. This is the code right here. It's just that. And all the way at the very end, there are the reset vectors. That's all you need to actually execute the code. Let's take out the dead test ROM that's in this machine and swap over to the new super tiny, hopefully helpful diagnostic ROM. Not 100% sure this is going to tell us exactly what I need to know, but maybe it'll help. All right, here we go. It didn't even switch into the text mode. Did I forget to actually flash this chip? Pretty sure I flashed it. Yes, I did. So that verify pass. I mean, it works on the emulator. So why isn't it working on here? I'm just going to write it a couple more times just to kind of overburn it. Hopefully that was all that was wrong. One more try. Oh, I should hook up the speaker because it is supposed to beep the computer. I don't know if that really works. Oh, there was a little beep. So the beep is working. Do you hear that? So beeps. Question is, why isn't it switching into text mode? And we're also not seeing anything on screen. So it's able to tick the speaker, that works. And we heard that on the other ROM, but it's not able to switch the graphics mode out of it and back into text mode. That doesn't seem to work. So writing to the speaker is C030. And then the text and the graphics stuff, this is all in this 50 stuff. Could this be the same address error that's causing the RAM to not test correctly is somehow affecting these writes or reads to these addresses? So I converted each of these hexadecimal values to binary, and I've pasted them in here. And we know the speaker one works, but the other ones don't. And for instance, as an example, I mean, it's hard to know exactly if we have any stuck bits here, but the bits have to look exactly like that for the speaker to work properly. Otherwise, we won't hear that tick out of the speaker. So for instance, if we have that bit stuck, and that would change it to 0, then it would make that read go to CO11, which is obviously something else, or nothing at all. And going to the schematics, that stuff that like changes the text mode and mix mode and whatever, it's coming from this F14. Now for the speaker generation itself, there's the speaker. That works. And we know that is coming from this chip, 74LS138. And notice it has these address lines going into it. But it's this chip F13 that's generating the chip enable for the one that's changing the video modes. And that only looks at these lower 4 address lines. what we should do is take a look at F14, pin 14, look at the enable line, and we should see it toggle low when the system boots up. I suppose we can also look at like the text mode output from this chip as well, just to see on pin 4 here, is this actually toggling? And then page 2 as well. So this is F14 right here. That's the LS259. Turn this off and let's take it out. No, you know what? Before I do that, let's take a look at what we see on the signals on this. Because obviously if I take it out, that's going to potentially make it work because we have bad contacts in this socket, for instance. Okay, so let's start here on pin 14. This is that enable pin. So we do have it toggling. And you know what? It toggles 4 times. And what does that match? That matches right here. We wrote to that chip 4 times to change the screen mode. So that actually coincides exactly what the assembly language code of the ROM says. Each time this hits, it should assert this chip, and then it should do stuff by looking at the address lines and then changing what's on the output. So I'm on pin 4 now. Let's turn this off and on. Nothing. What is this doing? If we switch this to auto trigger mode, it is just low. Let's see, that's pin 4, text mode. Pin 5, that's mix mode. Pin 6, and I'm on the sockets, by the way. I'm not actually on the chip itself. 2.27 volts, what? Oh, okay, this is interesting, everyone. I'm actually on the pin on the chip right now on pin 6. That is low, but on the socket, it's floating. So that feels like we have bad contact right there. And then this is pin 7 on the chip and on the socket. They're all low. Okay, let's go to pin 1. That's address line 1. Pin 2 has nothing. Pin 3 has nothing on it. Spiral cycle the computer. Okay, there we go. It's just the loop that the ROM is stuck in right now doesn't actually generate anything on that particular, on that signal. Okay, so let's check on the, this is on the socket. So now I'm on the chip. See, that doesn't look good. I think there's a bad contact with this chip. Okay, yeah, I'm on the body of the chip on pin 2, and that's not right at all. Pin 1, that's good. Pin 2, not good. This is pin 3, address line 3. Let's turn the computer off and on. Okay, that's fine as well. So pin 2 is bad. I think it's the contact in the socket that's bad. And again, these other pins, so this is pin 4 on the socket, and the chip looks pretty much the same. 5 is the one that's messed up. This is the mix mode output here. It's floating on the socket, but on the chip itself, looks like that. We've got our ripple from the power supply, but not on the socket. Okay, and then as for the outputs from the chip, 4, 5, 6, and 7, text mode, mix mode, page 2, and high res. This is text mode, pin 4 on the socket. On the chip itself, it's lower. So something's wrong here too. Okay, I got to take this out and we got to deoxidate it. I don't think the chip is necessarily bad, but we're definitely seeing shenanigans. You know, I said early on, maybe I just need to deoxidate every socket. And to be honest, that might just solve this computer's problem. Obviously, we had one bad chip with that bus transceiver, but clearly, I think we're having other issues. Okay, is there any difference here at all? Look at that. It's not fixed, but at least it's going into text mode now, which is what the ROM was instructing it to do. Yes. Oh, interesting. There's no more flashing. But the ROM is trying to write to, well, the ROM is trying to write to all the memory, and it's not writing to the memory. But I'm wondering if this is stuck in page 2 mode right now, not page 1. Also, another problem I'm noticing is that the color burst should be disabled right now. And it's not. That's why we're getting all this color fringing on here right now. Different problem, totally unrelated to what we're dealing with here. All right, so one problem solved. It was a bad connection for this F14. That's why the graphics mode wasn't changing. Now, as for writing to the correct page in memory, that is potentially a different problem. What I think I should do right now is we should take a look at what these signals look like coming out of here. I want to know if I'm on page 2 or page 1 right now. So on that chip, our problem child. So text mode, we're on pin 4. That is high-ish. I mean, it's at 3 point whatever volts, but that's good enough. If we turn the computer off and on, yep, it's low and it goes high. So that's working. So these signals right here, these are active when they're high. So that one should be high, that should be off, 7 should be off, and then 6 should be off as well. So 4 is on, 5 is off, that's mix mode, 7 is off, that's the high-res mode, and here is the key, page 2, 6, that is off as well. Because part of me was wondering if, for instance, this was outputting page 2, even though we have a text mode right now, what if we were looking at page 2, which is not where the boot ROM wrote to? The boot ROM wrote to page 1. So we definitely can tell, because, sorry, you couldn't see it, but I was probing all the pins on this chip, which just took out and put back in. And without a doubt, we are looking at text page 1 right now. And yet, all we're having is a bunch of question marks, which I'm pretty sure is exactly how the RAM is initialized if you power up the system. So in other words, all the writing that the ROM tried to do, the code in the ROM tried to do to the RAM, didn't actually work. None of the RAM got written to. Maybe what I need to do is we need to take a look at the RAM again, and let's look at the read-write pin, which is pin 3 on the RAM, and let's see if when I power it up, it at least toggles that line like it's doing something. Because right now the system is just stuck in an infinite loop. It's not actually writing. But when I power the machine off and on, yeah, look at that. It did actually write to the RAM. So we can go to normal mode. That will help us see it a little bit better. So yeah, look at all that. So this is the system attempting to write to the memory. So there's like a whole bunch of writes here. We would have to use a logic analyzer to really capture that a little bit better to see if it's really writing the right number of times. But let's just assume this is writing the correct number of times. I don't know why there are these gaps here. Maybe that's just normal for the Apple II. But yeah, there we go. Now what does need to happen when it's writing is the RAM DI pins, data input pins, these need to be driven as well. So let's look at pin 2 when we turn the system on and make sure that that's really happening. Oh, there's tons of stuff happening on here right now. So if we power this off, power back on, yeah, I mean, that doesn't really help us, does it? I think what I'm going to need to do is bust out a second oscilloscope probe. So let's turn on channel 2, just so I can see that when it's writing to the RAM, that we actually have some activity on the data lines. So I'm going to try to hold both of these probes this way while I power cycle this off and on. Okay, so when the write line goes low, that's when it's actually able to write to the memory. Okay, so there it was writing to the memory, and that line was low at that exact moment. Okay, we lost. Oh, this scope is so annoying. I don't understand what's wrong with this thing. Why is there an image up top where I could see theoretically what was captured, and yet it's gone now? Look, I can't see anything except for this tiny little spot here. It's like it lost its buffer. It looked like it was writing to the memory, and the values of the data inlines were changing, at least on that one data line that I was on, which was data line 7. Now, it's totally my hypothesis that the RAM that's in here right now, this is sort of like the power-up state. Like whatever was written into the RAM didn't get written to the right location. Therefore, even though, or I guess theoretically, what's also happening, oh, maybe I need to check this out. What if the problem is the circuitry that reads out the RAM and decides whether you're looking at page 1 or page 2, what if that's reading from the wrong place? What if this is page 2 we're looking at? Even though we saw on this one chip, page 1 is selected right now, but what if the circuitry that generates the video is still thinking it's looking at page 2, which just happens to be this garbage that's in RAM here? And I think if I switch out these Motorola chips for these AMD chips, we will go back to having those stripes. In fact, let's just do that, because I'm pretty sure what we're looking at there is just the uninitialized RAM that's inside this machine. In fact, what I could do is I could switch out part of this memory, like 2 of the chips, and it should change the way that looks, because my presumption is these AMD chips actually start up with a different pattern when they first get powered up. And page 2 is never written to, because the ROM only writes to page 1. Let's see what that does. Yeah, so right now the Motorola chips initialize to what is a question mark, except for the odd random junk. What is a question mark? But I switched out to these 2 AMD chips, and now whatever bits that these 2 chips are responsible for, data line 0 and 1, have changed the bits, the power on bits, which of course is in stripes, because we've seen before that these chips, these AMD chips, have stripes where it's probably all zeros, all ones, all zeros, all ones, except for the occasional like random junk in there. And if we go to my font editor that I have stuck on my GitHub repo, I'll put a link to this, I have loaded the actual character generator off of this motherboard into here, and everything was showing up as a question mark originally. And in fact, if we go all the way to the end here, I bet you it was this question mark that these Motorola chips show up. I think these initialize with all ones, and that would be a question mark, which is FF. Well, if we go to what we're seeing now, which was the less than symbol, that's FC, FF, and we know we changed out the chips for, I think it was this one, D0 and D1. There it is, FC. So yes, those two chips I changed out a power on sometimes to 00, and that creates FCs in memory, which we know from the font thing here, an FC is that. And that is exactly what we see here. So where the AMD chips power up with a 1-1, we still see the question marks, and where they power up with a 0-0, which was in these columns, kind of alternating 0-0, 1-1, 0-0, 1-1, we get the less than symbol. So without a doubt, what we are looking at here is coming from RAM. So the characters we see on screen here are coming from the memory. The question is the ROM actually writing into the memory in the correct location, but the video circuitry that reads out the memory to display on screen, is that pulling from the wrong location? Or is the video circuitry displaying text page 1 correctly? But when the ROM goes to write to text page 1, which is 400 hex, is it going somewhere else in memory? I personally believe that it's the latter. I think that the ROM is telling the CPU to write to the RAM, but it's going to the wrong place. And I think that might have something to do with why the dead test ROM doesn't work properly. You know, it's telling us there's a bad bit error, because I think what's happening is it's writing to the wrong place, and maybe it's reading from somewhere else, because the reading might be working. I don't know. What a complex issue this is. What a complex issue this is. All right, just for funsies, I put back the original dead test ROM, not the original ROM, but the dead test ROM, because now that we have the text mode, page 1, high res, medium res fixed, let's see what this thing does. Okay, so now I know the dead test ROM by default goes to text mode while it's doing the initial tests, and then when it does the beep to tell you which bit is wrong, it changes to mixed low res plus text mode, probably as a way to help you, in case your speaker's not working, like we can unplug the speaker and we can still tell we have one beep. I assume if we had 8 beeps, it would flash the screen 8 times. That's kind of clever, actually. Okay, so what I've done is I decided to change up this minimal diagnostic ROM to be a little bit more helpful in the case where I think that the CPU is writing to the RAM but in the wrong location. So unlike the other one, which just tried to write into text page 1, and it wrote 00 all the way through FF, and it repeated over and over again for the entire text page. Instead of doing that, what this does is it fills the entire memory on the entire Apple II, all 48K, you know, even though we have 2 banks that aren't even installed, and it writes to each memory location within that page the actual page number. So in the first 256 bytes of memory, it's going to write 00, and in the next 256, 01, so on and so forth, all the way through all the memory. So that's what's happening right here. You could see it had to be unrolled, right? Because we can't use subroutines. So it just writes all of this stuff. And what it does is it just increments X. So instead of writing to BF00, it's going to write BF into there. It increments X by 1, and then it reruns this entire thing over again. And that's going to write 86 to 8601, 87 to 8701, and so on and so forth. So now if we start this in AppleWin, there we go. We get D, E, F, and G. And that's because this is 400, 500, 600, and 700. That's what makes up text page 1. And the reason why it's interleaved like this is just the way the Apple II text mode and graphics modes work. Now going back to our text editor here, if we take a look at what is written here, 04, that's into page 4, that's a D, E, F, and G. Now this text editor doesn't show it to you, but it just so happens on the Apple II that this first chunk of characters, these first 4 lines, are inverted. Then I think we have flashing, and then I think these two, starting here at 80, I think this is not inverted and not inverted. But we're only writing up to BF anyways, so we would never actually see this upper range of characters, because the very last bank at the very top of memory in this top row, which we don't have installed, that would be a BF written to there, which would show up as a non-inverted, non-flashing question mark. So when I run this new ROM on this machine, if we get, say, flashing DEFG, then that's going to tell us that we're actually writing or looking at this page here, 44, 45, 46, and 47. And if it's not inverted, it's going to be 84, 85, and so on and so forth. Okay, so I've gone ahead and written that new ROM, that test ROM, into this EEPROM. Let's see what happens. Why don't we hook up the speaker, make sure we get the beep out of it. Here we go, 3, 2, 1. Aha, we got nothing. So the idea that the CPU is not actually writing to memory at all is actually kind of proven what's happening. I mean, this ROM is telling the CPU to write to all of memory, and none of RAM is getting written to, because if it would, we'd see it. We'd see it right here, and it's not. Look at that. How interesting. Now, if you're wondering how it's beeping, the beep actually doesn't require a write. That works on a read, and that's what's happening. It's actually reading from that memory location, because that's all you need to do is read from CO30 or whatever it is. And the same for the text pages and stuff like that. So it feels like writing is just not working. Now it's weird because we saw the write line going low, going to the RAM, so it should be writing, but it's not. I mean, it's strange to me. That's really strange, because even if, for instance, the buffers that are on here weren't being turned on at the right time when the CPU is trying to write, I would think that the bus would float or something like that, so something would get written to the RAM, but nothing's getting written to the RAM. I really believe that nothing's getting written to the RAM, which is why our RAM test fails on the dead test ROM and why the main system won't initialize with the original ROM. But what could cause this behavior for it to not actually write to the RAM? This is such an interesting, curious problem. I mean, I wonder if it's just totally due to the bad sockets, maybe, but all right, I'm going to stop and think for a little bit. All right, it's the next day, and I had to think about the problem, and I've taken a few notes here as to what I think I need to check next. So one of the things that I think might be going on is that the RAM write cycle is somehow not working. So when the CPU goes to write to the RAM, as instructed by the ROM, it doesn't actually get to the RAM for some reason. But I completely neglected to try out a tool in my toolbox that can help me identify if the CPU is actually writing correctly to the correct memory location, at least as far as the CPU is concerned. And it's the Apple II VGA card, which I used a lot during the troubleshooting exercise for the Apple II GS. We know that the buffers for the address lines and the two transceivers for the data lines are probably working correctly. And when the CPU goes to write to, say, the RAM, like to the screen location, well, all of that stuff is also mirrored onto the expansion slots. So if I plug in the Apple II VGA card, it should be able to see and snoop on that write activity that should be going to the RAM and then display it on this VGA connector. This does not rely on the actual RAM or video subsystem on the motherboard from working at all. So if the problem exists in the RAM circuitry, like the address multiplexers or whatever is generating the signals that the RAM uses to read and write, well, this card, it shouldn't matter. This should allow us to see that the CPU is executing code and is going to fill the screen with that DEFG that we saw from the emulator. Here we go. I'm going to turn this on. Well, interesting. Now, one thing about the Apple II VGA card is when it first powers up, you're just going to get random garbage. And we will have seen that there. You saw some random garbage, and then it cleared. And what's confusing to me is what we're looking at on screen here is exactly the same thing that we're seeing from the RAM itself. And I was under the impression that what we were looking at on the composite video output for this motherboard was just the uninitialized state of the RAM. But something on this computer is taking what's in the RAM and copying it to this card. Wait, I'm so confused about what's going on here. This is a very unexpected result. I was totally just expecting to see the DEFG like we had on the emulator. Not this. And the funny thing is I'm pretty positive that what we're looking at here is coming from the RAM. If I take out these two AMD chips that we have on the side here, now we get all question marks. So like there is an effect. So if I take the ROM out entirely, and we turn this on, then we just get the garbage that is natively coming out of this Apple II VGA card. So no ROM code is doing anything. So something in that ROM code somehow is initializing the VGA card to have the same output as the RAM. What? I'm so confused. This makes no sense. All right, so the two AMD chips are back in. I'm going to put in the dead test ROM, the original unmodified code. So this is behaving identical. I'll take the speaker off. Identical to how it would be on the composite video. We're just looking at, by the way, the green that's on here. There's a setting in the Apple II VGA card lets you set it to monochrome mode, which is obviously how it's set up right now. Just ignore that. This behavior does not make sense. I would have never in a million years expected to see what we see in RAM and the composite output to be mirrored exactly on the VGA card. In fact, if we switch back to composite video, which will take a second here to sync up the HDMI input, I mean, it's the same. It's literally the same. Like we have a flashing slash and a question mark on the top right corner, and a flashing slash and a question mark in the top right corner. Whatever's in the RAM is being mirrored onto the expansion slots, and it's being picked up by the Apple II VGA card. Just trying to understand what could cause this exact symptom. It's as if writes to the RAM are actually being treated as reads. Okay, I think I'm starting to understand what's going on. So when the CPU tries to write to the RAM, it actually causes the RAM to write back to the bus, which might explain why the VGA card just ends up seeing what's in the RAM. It's actually copying the RAM contents back to the bus. So this would indicate that the bus transceivers are operating in the wrong direction. Like they are stuck in a direction that always reads from the peripherals, and it never actually goes from the CPU back to the peripherals. Okay, I think this is a breakthrough right here. I think so. So let me try to explain that a little bit better here. So here's the 6502. These are the bus transceivers. Remember, they can operate in either direction. They can either operate with the signals from the data lines going into the CPU, or they can operate the other direction. They have to operate in that direction where it goes into the CPU anytime it's reading from ROM, which we know works because it's able to execute code and beep the speaker. But also anytime it's reading from the RAM or reading from anything else, it needs to go in the direction it points to the CPU. But what if it never is working in the other direction? And specifically, that is controlled by this chip right here, 74LS32. I need to take a look at pin 8, going into all of these things and make sure that it's actually swapping directions. But let's think about this a little bit more. If the read-write signal were properly getting to the RAM at the right time, then the RAM wouldn't actually be reading out anything. It would just be sitting there, not driving the bus. It would be waiting for something to come into it. But the RAM actually seems to be operating in a mode that is reading, even though the CPU is trying to write. I don't think it's this output here, because we were able to see the output on this pin working properly. But I guess we should at least take a look at pin 8 here, or at least pin 1 on any of the two transceivers. So let's make sure that that line does toggle properly, because it must not be. It cannot be. So that kind of implies that we do have an issue here, or this chip is bad or something. Let's first look there, because no, actually, wait, let me think about this. So even if these are trying to drive the bus, and they're conflicting with the RAM, it's possible the RAM is just more powerful and is able to override these transceivers. So if we look at pin 1 and we see it actually going low, I think it's a low, yeah, it's low when it's going to be writing to the bus, like CPU this direction. I bet you there's bus conflicts happening because the RAM is also writing to the bus at the same time, and that's what the Apple II VGA card is picking up. I think that's where our problem is. Now, you might be asking, like, well, how can it set text mode and beep the speaker? Well, it doesn't actually need the data lines at all to do that. That's simply based on addressing, and that's it. You just have to read one of those addresses, like for the beeping the speaker, or, well, it takes the speaker, or switches modes. Doesn't rely on this stuff at all. But if we take a look at the RAM, which I think is operating in the wrong direction. Oh, is this the same chip, by the way? 74LS32. This is what's taking the read-write signal and Phi 1, which is one of the clock signals, and that's going to the right enable pin for the RAM, C14. That is interesting. So it is the same. Now, last night when I was reading this document, one of the things that is very important is the timing for writes to RAM. So the way the sequencing has to work for these types of DRAMs is first the write signal goes low, and then the RAS signal goes low. Then you set up what's on the data bus right here. So you have to set the input into the chip on the DI pins, and then the CAS line goes low. And it's right here where it goes low. This is where the RAM picks up what's on the data bus and stores it in RAM. If for some reason the write signal isn't happening at the right time, like it goes high before the CAS signal goes low, then what's going to happen is the RAM will read out, and it won't wait for something to come into it. It will actually just read out. This write signal needs to be low at the exact same time that this CAS goes low when a write is happening. If there's something wrong with the sequence, like I know I saw the write line, I'm pretty sure I saw the write line on the DRAM going low, so that's happening. But if it's happening at the wrong time and it's not happening in concert with this CAS going low, then the RAM will read out as opposed to be written to. So I think the first thing I really need to do is we need to take a look at C14 and take a look at this pin 11 that's coming out of it, and I guess pin 13 going into it, and the clock signal. And we just need to make sure all of those signals look correct, because this is the only thing that really generates the write signal that goes to the RAM. That's it. It's just this gate. And of course, it also has to do with the direction of the transceivers, that same gate, just different pins. And it's also gated to Phi 1, and it's gated to the read-write signal. So it's acting just like the DRAM part of it. First things first, I need to look at that chip. Yes, we need to do that. Oh, it's this one right here. I have my finger on it. That was quick and easy to find. All right, so first I'm going to go on the body of the socket, and I'm going to turn it on, and we're on pin 8, so this is the signal that is controlling the direction of these transceivers. Okay, there's activity there. Okay, so what's interesting here is while there is a pulse that's happening sometimes, oh, you know what? Let me switch back to my other diagnostic ROM, the one that should just write to all of memory. Because I think the problem with the dead test ROM is it's failing immediately, and it's not really writing to that much memory, and we want to write to all of memory, because we'll see more activity here on this pin. Okay, so pin 8, write. A whole lot more writes as it tried to fill up memory. So that's good. That tells us that this signal, at least on pin 8, looks correct. All right, now let's check pin 11 for the DRAM. Power it on, and there it is. What's weird is, do those look longer, those pulses? This is pin 11 versus pin 8. They do. Why? There's no reason for that. Ultimately, the inputs to this gate is read-write and Phi 1, that's on pin 11, and the one that looks skinnier is Phi 1 and read-write. Same thing, and they're both connected after this H5 gate here, so read-write. Why is there a difference? There should not be a difference. They should look exactly the freaking same, exactly the same. Let's just check that one more time. I'm on pin 8. And you can see very skinny pulses, lots of them though, but skinny. And now if we go to pin 11, much wider pulses. I think the cadence is the same. Like you'll see they're that far apart. We go back to pin 8, turn the computer off and on. Yeah, so same cadence, but why so skinny? I almost feel like the issue is the pin 8 here. This is turning off these transceivers like in the middle of the write. They're like flipping directions or something like that. Whoa. Okay. So I think this chip is bad. I just put some deoxide in that socket, and let's put it back in. I don't think it's going to make any difference whatsoever. I think the problem is this chip is faulty. So let's see. I'm on pin 8. I mean, it looks exactly the same. And now I'm on pin 11. Longer pulses. Okay, I went into my parts and I found another LS32, the one that has the tick mark on it. With it in the board, let's check to see what pin 8 looks like now when I turn it on. Skinny pulses. And we look at pin 11, long pulses. Okay, well, I think what I didn't do is I did not look at what pin 9 and 10 look like. So here's 8, the skinny pulse. 9 has long pulses. And we'll look at 10, which is what? Clock signal. There's nothing on it. Wait, what? There is nothing on pin 10. There is nothing on pin 10. That should be phi 1. Why don't I go to the CPU and look at pin 3? So there's pin 3. Literally what this should be connected to directly to pin 10 on this chip. But I go to pin 8, 9, 10. Oh, what? Now it's there? I saw it a second ago. What is happening here? The computer's on. Again, pin 3 on the CPU. There's our clock signal. And I go to that pin on here and it's not there. All right, well, let's check the other one because it's on multiple pins, right? We know it's also on pin 12 and it's got it. It's got it right there. Wait, what's happening? I don't understand. Is this just like a totally bad socket? 8, 9, 10. Pin 10. This is what I'm on right now, and there's nothing. But I swear it was there a second ago. Pin 10, phi 1. I think we have a bad trace on the motherboard potentially. Well, maybe I just need to bodge it over. Let's look at the bottom side and just stop. This has got to be the problem, right? Oh, you know what I can do? I am just going to literally bodge this over from the other signal that's right nearby. And I guess I can put back in the other chip because there's nothing wrong with the other chip. So pin 10 and pin 12 should be the same signal on this chip, the phi 1. So we'll just connect these together like this. Now let's take a look at pin 8 and look at those pulses when I turn it on. They are long now. They are not short and skinny. Okay, I'm back on composite video output, so we're just looking directly at the video circuitry. Let's see what happens when we turn it on. Look, it freaking works. That fixed it. That freaking fixed it. That is unfreaking believable that was the problem. And that was not just like a bad, dirty socket or a dirty chip, because I swapped the chip. There's deoxit in this socket. There's a bad connection, I think, under the socket that's causing this to not work. So that right pulse was way too short because the clock signal was missing from that gate. And what was happening is the bus transceivers, because we were looking at pin 8, it was flipping the direction of the bus transceivers somehow in the middle of the actual write sequence. And that's why it was never writing to RAM. I don't fully understand how the RAM was ending up back on the data bus that would be picked up by the VGA card. But obviously we saw it happening. The RAM contents were somehow being read out and then picked up by the VGA card. What we're looking at now is the VGA card output. Let's turn it on. There it is. So that was it. That was the problem the whole time. What a weird, obscure issue. Wow, that's just hard to believe, isn't it? I'm editing the video and I'm sort of thinking about what was happening, why the VGA card was showing the contents of the RAM. I think what was happening is because that pulse that was turning the direction around for the bus transceivers was so short, it wasn't really doing anything. So they were essentially always in read mode, never going into write mode. And the reason why the VGA card showed the contents of the RAM is because the VGA card was getting a write signal, a read-write signal from the CPU. It was getting that. And it picked up whatever was on the data bus, which actually was an open bus situation because the bus would be floating right now because the CPU was trying to drive it, but the bus transceivers were set incorrectly. Well, what often happens when you have open bus is that the very last thing that was on the bus, it's still there because of the capacitance of all the traces and whatnot. And the last thing that is on the data bus is the RAM contents for text page 1, because that's what the video circuitry is reading out of the RAM. It's constantly doing that 60 times a second. So the VGA card, when it saw the write to RAM, it just looked at what the data bus was. Well, the bus was floating, and it was actually just picking up what the last read from RAM was, which just happened to be what is text page 1. And that's how I think the VGA card was getting a copy of text page 1. Hopefully that makes sense. Well, I'm going to go back to the original dead test ROM, and let's see now if this is able to test all the RAM properly. All right, here we go. Yep, there we go. I mean, the video looks like garbage because there's other problems on this board, but from a functionality standpoint, we are freaking working. Let's put in all this other RAM back in the board. I guess I should deoxit these sockets, you know, just for fun. So it just sort of shows you that you can't just blindly trust the diagnostic ROM to tell you, hey, you know, RAM is bad. I mean, it was telling us bit 0, bit 1 was bad. Early on, we determined that that was not the case and that there was a bigger problem on this board. Still surprised about what's actually going on here. I wonder, I mean, there's a couple solutions I could do. I could just bodge a little wire underneath here. I could replace the socket. I'll probably just bodge it because I'd like to keep these sockets original if possible. It goes without saying that this system should boot right now into AppleSoft Basic without any issue whatsoever. I'm just noticing that this RAM chip has a folded over pin. Was that me who did that? I don't think so. This was one of the chips in the middle of the pile, which I didn't touch, like since I took it out of the board. I don't think this thing would have worked properly with a bent pin this way. It's entirely possible that someone was monkeying with this thing, trying to get it working before I got to it and folded over that pin. But I'm 99% sure that that folded over pin was not from me, specifically because that was one of the chips that I took out. I think I took it out of this middle bank, and I never really touched the middle bank. I wasn't like swapping chips in and out of it at any point. Oops, my little bodge just came off. So the system will not work at this point. Or maybe it will. Maybe it'll just magically work again. Oh, I need to put back the original chip that was in there. Okay, out with the replacement chip, in with the original. And there's a bunch of deoxit on these chips. I'll just clean that off in a bit. I assume when I turn this on, it's going to tell us we have bad RAM. Let's make sure I have all the RAM in correctly. Okay, I think everything looks good here. Let's turn it on. Yep, bad RAM. Because we are missing our little jumper link. This is our chip, and we need to hook up pin 10 to pin 12. Let's see if we have connectivity between those two pins. Let me make sure I'm on the correct chip. Yes, that's it. 8, 9, 10, 11, 12. Yeah, it's these two pins should be connected. And that's what I had connected, and it was working. And now it is not. So 8, 9, 10, 11, 12. Nothing. No connectivity. And that's in continuity mode. Okay, there's my little bodge. I put it where it can't touch any of the traces. You know, it's not over any traces because it's just a little piece of unprotected metal. Okay, let's hook this back up to power and see if we have a working system. We do indeed. That was the problem. So there's actually a broken trace on the board there. There's nothing wrong with the socket. There's nothing wrong with the chip. There's a broken trace under the socket because where I bodged over, there was nothing connecting those things together. Unbelievable. Last time I worked on an Apple II clone, we had issues like this too, where there were like slightly marginal traces and whatnot. I guess it's just like bad quality PCB. And just so everyone can see that with the Apple II VGA card, this will be working correctly. Here we go. Yep. All right, well, that's going to be it for this video. This was quite the session, I gotta say. Very gratifying to find the actual problem that kept this thing from working. Obviously, I haven't booted an OS yet, and we have other faults that we got to deal with. Something wrong with the color. I don't know if the keyboard works. I don't know if the keyboard part of the circuitry works at all. That could be broken as well. So we might have more issues with this board. But at this point, I am 100% positive that it will run code without issue. So I can put a disk controller in here and we can boot up an operating system and it will work. Now, I can hear people saying right now that this video was way too long. I should have just deoxidated every chip and it just would have shortcut half of this stuff. But the reality is it wouldn't have really fixed anything. There was only one chip that had dirty contacts that was keeping this from working. And it was that one that had to do with the text page and the graphics stuff. But this LS32 I just fixed, that's not a dirty socket. That is a bad trace that's on this board. And of course, we also had this bad bus transceiver that I was able to identify and fix in part 1. There's something to be said about these original Apple II Plus motherboards in that they are so full of chips and all these TTL logic chips, it just can present really interesting and subtle problems. When you have large chips like on a 64 that do so much and you're like, oh, there's, bad video. It's just the VIC2 chip. You just swap it out and you're working again. Well, everything's discrete TTL logic here. That means you can have these really subtle little weird issues like you just saw me go through, and it presents a really interesting challenge to try to get these fixed. Now, in the case of this motherboard, you could have swapped out every single chip with new chips, like from another working motherboard, and you still wouldn't have had a working system, right? Because we had that bad trace. So this thing really threw the kitchen sink at me when it came to potential issues. Bad contact in the socket, bad chip, and bad trace. I mean, there might be more issues on this board too. There probably are more issues, and that'll have to be for the next part. But I have to say, at least for me, getting this thing working, I mean, to this point at least, has been really, really gratifying. And I do wonder about that folded over RAM chip. If someone had been trying to get this working before with this bad problem with the bad trace on the LS32, and they had taken all the RAM out, moved it around, and all that stuff, and they folded that pin over, which would have made the system, well, if it was already broken, it wouldn't have been any different. But that's just an interesting fault as well. It's one of the dangers about taking every chip out and putting them all back in is you can easily fold it over and just not notice. These sockets are especially hard to see because they kind of cover the sides of the chips, the way the socket design is. So a folded pin like that, you wouldn't be able to see it without literally taking every chip out and inspecting. So I really do wonder if someone had really struggled with this board in the past and, well, at least now it's actually freaking working. How awesome is that? So if you like this video, I'd appreciate a thumbs up, but if you didn't, you know exactly what to do. Subscribe, comment down below. Thanks to my supporters, all the usual YouTube stuff. And thank you for Ricardo for sending these machines to me or donating these machines to me. And then thank you to Vax11 for sending these things to me so many years ago. I still have, the 4 other machines that are all in unknown state. Some of them have every chip taken off the motherboard. So I assume we have problems there too. So there's lots more to do on Apple II, but people may be burned out with this type of troubleshooting. Now I've had several videos in a row just like this. Maybe I need to go to something easier for a little bit. So let me know in the comment section. And I guess that's going to be that. So stay healthy, stay safe, and I'll see you next time. Bye.